we are planned to do a practical regarding first law of thermodynamics here, right? So before starting that one, we will just discuss about the first law of thermodynamics first. Okay. So already we know this first law of thermodynamics is very related to the energy conservation. So actually the energy conservation is the first law of thermodynamics, or we can call as first law only. Or so as we know from our childhood, we have studied the conservation of energy concept. That is, energy can't be created or destroyed, but it can change into one form to another form. So that's actually the first law of thermodynamics. So we are going to discuss. Already we have discussed about several terms of energy concept. So as internal energy, heat, and work. So in most of the engines, all these concepts are we have to consider. Okay, when engines performance and those stuffs are there, when we are analyzed with the thermodynamic analysis, we are consider about the internal energy, heat, and work. So we are going to discuss the first law of thermodynamics in the forms of internal energy, heat, and work. So how it's related is, so internal energy change is delta U is equal to heat coming into the system. Heat coming into the system. That means if you are combusting something, okay, fuel, let's say fuel, so heat is you are producing. So that is coming from outside. So that is heat coming in minus work going out. That means that is what your engines work output. So this is actually the relation between internal energy, heat, and work. So as we know the energy conservation, so that is actually the energy conservation. So energy conservation tells us the energy change is equal to energy come in, E in, minus energy going out, E out. So now we can relate these two concepts together. So those are not actually different, those are same. So our task today is to just to relate this concept with a small practical example. Okay, so let's do the practical first, and then I will explain the observations. What's the observation related to this concept? Right? So I will explain what's the practical we are going to do. We are having a model, that's a bottle and a balloon concept. Okay, small bottle and balloon is fixed. Now we are going to give a heat to the system. So now we are having a system like this. Okay, so system is a bottle and the balloon. So now bottle is like a rigid boundary. So this boundary can't be moved. Okay, so I mark the system boundary. So this is a closed system, balloon and the bottle is a closed system, and balloon has a boundary, and also bottle has a boundary. Bottle is rigid boundary, but the balloon is movable boundary. That boundary can be moved when balloon is blowing up. When balloon is blowing up, the boundary changes. So we can say the balloon's boundary is a movable boundary. So internally only air is there. Only air is the system. Okay, air is the system. So you are having two type of boundary. So now what's the concept is, we are going to give heat. We are going to give heat and see whatever going to happen inside the system. So now the water is boiling. So let's wait for it boils. So before that we should know the properties of this air. So this is going to be in pressure atm, and a given volume, let's say volume 1, right? And it's going to be temperature T1. So these are the initial properties of this system. So when we are giving heat, as the heat is process related with the process path, so that this heat is a path function. So your properties is going to change. Properties are going to change. Okay, when the properties are changed, we can see whatever changes will be in the system. So by our naked eye, we can see what are the changes will happen in the system, and then after the observations we can discuss the what is actually happened related to the thermodynamic first law. Okay, so by using the first law of thermodynamics, we are going to explain this phenomena, right? So we'll wait for a while. So now the water is boiling. So now you should see the system. Okay, this is your system. I am going to dip this water to this system in the water, that I can give the heat to the system. Okay, take the observation. Now you can see, when I give the heat to the system, this balloon is blown. Okay, this is first observation. Now I give the heat to the system. Now system get heat. Okay, now the second step, I am going to release the heat from the system. Okay, I am going to release the heat from the system. So what I can do is, so for a heated system, I can release heat from dipping in a very low temperature. So that means room temperature water. Okay, so room temperature water I am dipping. Now you can see the balloon is going to initial state again, right? So these are the two observations. First of all, I am giving the heat to the system, then I release the heat to the system. So two observations you made. I am going to list out the observations. observation. First one, when you are giving heat, balloon blow. Okay, so that means volume of the balloon or the system increase. Second one, when removing heat, volume of the balloon or the system decreased. Okay, these two observations are there. So how the balloon blow? Okay, how the volume of the balloon increased. So if you want to increase the balloon's volume, that means so you have to blow it. So when you are blowing, what you are doing is you are working against the balloon's stiffness. Okay, you are working against the balloon stiffness. So that means somehow you are giving a force to make it extending. When the when the volume is increasing, the length is increasing. That means you are working against the stiffness of the balloon. Okay, so there is a work is involved. There is a work involved. Okay, so same stuff when you are releasing the, now you have blown, when you are releasing already there is a force. So when you are releasing, now the extension is releasing. That means balloon is working with the stiffness. Balloon is working, right? So that then only it come to initial position. So in these two observations, work is there. First one is balloon is blowing. That means there is a work on the balloon. Okay, or from inside there is a work against the balloon to blow it. Okay, so when the volume decreases from outside on your balloon, some work is happening. That means that is because of the atmospheric pressure. Okay, when you are releasing the heat, inside pressure is decreasing. So when that is going below to the atmospheric pressure give a force to decrease the volume of the balloon. So that is the concept. So now we can go to the first law and do the analysis regarding this one. So as I said earlier, delta E is equal to E coming inside and E going outside. That is the energy conservation. So this is your bottle. When you are giving heat, this balloon is blowing. So that means your system is working. Okay, when you are giving heat, your system is working. That means you are getting a work output because of the system. So because of the pressure inside and temperature inside uh, increases, right? Because of pressure and temperature increases, volume also increases, right? So that is because inside pressure is when inside pressure increases of the inside pressure of the molecules increases, external pressure is PATM. So when PATM is low, to make this as PATM, right? To make this as PATM, volume will increase. Okay. When volume is increasing, your system is working. System is working against the balloon stiffness to extend this surface area. Okay. So your system is working. That means work output comes. Heat input you are giving. Okay. So what is the internal energy change? So as the conservation of energy, internal energy change should be equal to heat, you are given heat of HOQ minus work out, right? Work out. So that is, so after this working procedure of your whatever your system, internal energy change is equal to whatever your heat is given minus whatever the work output. Work output means work that used to extend the balloon surface area. Next one, for the next observation, when you are removing heat externally, work applied on your system to shrink it. That means your volume of the system decreases when you are removing the heat, right? So there is a work in work, so some work is done on your system, earlier work done by the system, so you are getting a work output. So here you are, so someone the I mean the uh, atmosphere is giving a work, okay, giving a work on your system to shrink it. So that is the work in, okay, work in, work applied on your system. So that is you are removing the heat, Q out. So what is your internal energy of your system? Internal energy is delta U is whatever come in minus whatever go out. So in minus Q out. So now also your energy is conserved. So this is your internal energy change for this system. This is your internal energy change for this system. These two are giving your energy conservation. Principle, right?